Yeah, that's a good question. So, in principle, of course, it depends on the application, as you say, right? If we're talking about a running shoe, there are multiple objectives. One of them is, of course, you want to get a forward boost. You want to ideally move forward, and there's the so-called shear normal coupling, which is interesting. So, if you step onto it, it should ideally give you a boost forward. And this is something that mechanically we can induce if we make sure that there is a coupling between normal incidence and the shear behavior, then this can in fact give you a slight boost forward. But there are many more other aspects that are interesting. For running shoes, for example, one of the prime objectives is not so much giving you the extra boost, but making sure it's comfortable for the foot. And what this means is that different parts of your foot, they actually want to have a different response from the shoe. The back, the heel, wants a different stiffness, a different energy absorption in the midsole than the front of your foot. And so, from physiology, one can figure out. We don't work on the physiology, but there are teams who look into this. What would be an ideal response that a shoe at every point should give to the foot? And this, in a way, tells you how you want to design the shoe. So you basically say, if I impact it, I want to have a certain force displacement curve or stress strain curve. So if I dip into it with a certain force or with a certain displacement, what is the force? And this gives me a curve. And this curve I can determine, or physicians can determine for different parts of the foot. And then it's our job to basically come up with an idea of how to design structures that follow exactly that performance, that give you exactly this feeling that you want. And so for a number of years now, we've worked with a major shoe producing company, uh, and there it's basically all about they know what kind of force displacement curve they want, but how exactly to make the structure that gives you that behavior, that's the challenging part. And this, of course, goes far beyond just shoes. So running shoes is one example that you can do at mass produce. But think, for example, about patient-specific objects, be it a patient-specific foot shoe, because you have a foot injury and you want to take into account that that your shoe gives you the optimal healing process. A very similar application is in bone implants that we also looked into a while back. If you want to make a hip implant or a knee implant or something like this, I'm a by training I'm a solid mechanician, a mechanical engineer. I'm a scientist who's working on trying to discover new materials. Who lives in Zurich and enjoys Switzerland, but also works with all kinds of people around the world and enjoys people from all around the world.
So can you tell me about your lab? I think I told you the what made me interested about what you have been doing, the shoe design and the bike helmet. I think that's kind of daily use cases that we can use in our life and using the artificial intelligence and the material, the mechanics of the material. I think that's where I think very interesting what you have been doing.
Yeah, of course. No, of course. So I work at the intersection of engineering mechanics and mechanical engineering, also material science, a bit of computational science. And what we essentially do is we try to understand why materials behave the way they do and how we can make new materials that have interesting properties, interesting functionality. And maybe if you allow me to elaborate a bit more, classical materials, of course, have their properties. If you design anything from a shoe to a robot to something else, you have to use materials for that, and every material comes with properties and functionality. This can be stiffness and strength or toughness. It can be energy absorption or things like that. And what we classically do is we take the materials that are surrounding us on Earth, or we go to lookup tables and try to find the material that matches best our application. And of course, then very often you have very particular properties you may want. For soft robots, you want software configurability. For biomedical applications, you need materials that mimic, human parts as well as possible. You very often need special performance. And the problem is that the natural materials we have on Earth are highly limited. We have a long list of materials from metals to ceramics to polymers that we can use, but the range of properties is limited. And this is where so-called metamaterials or architected materials enter the picture. And the idea there is that you make materials that don't exist in nature or that have properties you cannot easily find in nature. That's where the name meta comes from. Meta is Greek for beyond. This is where it was originally introduced. The idea is, can you make materials that have interesting, peculiar, extreme, whatever properties that you naturally cannot find? And this can be anything from, interesting, very light materials that have high stiffness and strength, or materials that guide waves, materials that absorb impact energy, materials that are anisotropic, so they have very different behavior in different directions. materials that resist fracture or that suppress vibrations or things like that. And the way this is typically done is that we think about these metamaterials not in terms of classical materials that are made of atoms and grains and whatever, but we make structures. So a metamaterial is nothing else but a structure. It's a structure that's put together out of beams, out of plates, out of shells or whatnot. This was enabled primarily based on additive manufacturing. We can easily make these kind of structures. But now the interesting point is based on how you put the structures together, how you connect them, how you shape the geometry, you can really design the properties and you can make properties, functionality, performance that you don't naturally find in classical materials. And this we work on a lot. We've worked on a lot over the past or many years now, more than 10 years on so-called metamaterials, architect materials, among others. And the point is making structures that have interesting behavior, interesting time-dependent behavior, interesting static behavior for all kinds of applications.
So what kind of material do we have in this structure? This let's structure, right?
So yeah, this one over here, for example, is a polymeric structure. Is a relatively simple 3D printed structure. It's highly viscoelastic, meaning it's time dependent. Of course, you can make all kinds of things. This is a relatively stiff structure that we have over here. It's a bit hard to compress, hard to deform. It performs differently in different directions. You can also miniaturize those as a relatively stiff thermoplastic. And based on the base material that you use, these are all 3D printed, but especially based on the architecture, we can make different properties. So here is one that, for example, is excellent for energy absorption. If you drop an object onto this, even an egg might not break because this absorbs so much energy. You could also use this for a time-dependent behavior. So you make structures, but afterwards you deploy them, and it will take a certain time until they go to the shape that you want. Um, and so these are 3D printed polymers, thermoplastics, and whatnot. But nowadays, you can use almost anything. I mean, people have made small scale structures out of metal, out of ceramics, out of carbon, out of, well, I think this field of actually making them is still growing and is still expanding rapidly. What we work on a lot in my lab is trying to design the architectures, assuming that either now or one day we can make them. What would the structure have to look like so that it has certain properties, and then we can print it, we can test it, and so forth.
Maybe the quick question: the material and architecture. How do you see the significance when it comes to designing metamaterial? Assuming that we have certain class of material that limited you, do you think the material more significant or the architecture when it comes to the design process?
In this case, it's absolutely the architecture. I think this is the big advantage we have over classical materials. So in a classical material, if you take a piece of metal or whatnot, what determines its properties is the composition, what material is in there, is the grain structure. If you zoom into a polycrystal or so, is defects and whatnot. But the problem is those are very hard to manipulate because if you want to move atoms around or you want to change the small scale defect structure in actual in a piece of metal, it's hard to do. If I want to change the arrangement of beams over here, it's really easy to do. All I do is I change my design. I tell the 3D printer to print it differently, and this is very easily to be manipulated. Of course, you make a good point. The base material itself also changes the properties. So if I make this out of a polymer, or if I make this out of a metal or of a ceramic, of course, by the end of the day, this also changes the properties. But the nice thing here is that I can really design the properties based on how I put the structure together. And I have enormous flexibility in doing so, which I don't have in classical materials.
Mhm. So can I give example? For example, maybe we can go for the shoe or the bike example, the helmet design. You told me that you're designing the metamaterial to achieve properties doesn't exist in nature, and maybe the first one, how you decide what kind of properties that you need for the design, assuming that make the shoe run faster, whatever, or the or pressure distribution. So what exactly you're looking for and how you achieve that? Maybe that's the first part. Yeah.
Of course. Yeah, that's a good question. So, in principle, of course, it depends on the application, as you say, right? If we're talking about a running shoe, there are multiple objectives. One of them is, of course, you want to get a forward boost. You want to ideally move forward, and there's the so called shear normal coupling, which is interesting. So, if you step onto it, it should ideally give you a boost forward. And this is something that mechanically we can induce if we make sure that there is a coupling between a normal incidence and a shear behavior, then this can, in fact, give you a slight boost forward. But there are many more other aspects that are interesting. For running shoes, for example, one of the prime objectives is not so much giving you the extra boost, but making sure it's comfortable for the foot. And what this means is that different parts of your foot, they actually want to have a different response from the shoe. The back, the heel, wants a different stiffness, a different energy absorption in the midsole than the front of your foot. And so, from physiology, one can figure out. We don't work on the physiology, but there are teams who look into this. What would be an ideal response that a shoe at every point should give to the foot? And this, in a way, tells you how you want to design the shoe. So you basically say, if I impact it, I want to have a certain force displacement curve or stress strain curve. So if I dip into it with a certain force or with a certain displacement, what is the force? And this gives me a curve. And this curve I can determine, or physicians can determine for different parts of the foot. And then it's our job to basically come up with an idea of how to design structures that follow exactly that performance, that give you exactly this feeling that you want. And so for a number of years now, we've worked with a major shoe producing company, uh, and there it's basically all about they know what kind of force displacement curve they want, but how exactly to make the structure that gives you that behavior, that's the challenging part. And this, of course, goes far beyond just shoes. So running shoes is one example that you can do at mass produce. But think, for example, about patient-specific objects, be it a patient-specific foot shoe, because you have a foot injury and you want to take into account that your foot, that your shoe gives you the optimal healing process. A very similar application is in bone implants that we also looked into a while back. If you want to make a hip implant or a knee implant or something like this, then you want to have a structure whose properties are as close as possible to human bone. Because in this case, you have it's clinically known that if the implant has properties very close to human bone, then you see less bone loss, you see less atrophy, you see less issues, long-term issues that the patient may experience. And so again, you want to design something that's physiologically as close as possible to what you ideally want. And in these cases, it's interesting to do the inverse design. That's what we call it, where you basically say, okay, I have a design space, I have a certain base material. And now the question is, how do I fill this design space? How do I make the structure so that the property at the end, be it the force displacement curve, be it a stiffness or something like this, matches the target that we had at the beginning?
Hmm. So I assume you have to have a scan for the foot, like in this area, like the heel and every region to determine the profile of the foot displacement about what you're trying to do, and then you make the
That's an
inverse.
option. I mean, we personally work on the inverse design, which means we never see a shoe or a foot from the shoe producing company. We work on the inverse design, but they basically come to us and say, this is the force displacement curve that the foot wants, as has been determined by physicians and therapists and whatnot. Can you make a structure that has this? And then we basically come up with design approaches. Um, Maybe that's also one thing I can explain. The this inverse design problem is a very hard problem to solve in general. Um, we have a forward problem and an inverse problem in my field, in our field. The forward problem is if you give me a structure, I'm supposed to figure out what the properties are. And this is a problem that's relatively easy to solve. Number one, you could do an experiment, of course. Number two, you could also perform a simulation. You try to model the structure and see how it behaves. And this is the so called forward problem. And this is an easy problem, I would say, because this problem is what we would call a well posed, which means if you give me a structure, there's a unique correct answer. And if I run a simulation and it matches the experiment, then I know I have the right answer. This is how it behaves. That's just the truth. The inverse problem is exactly the inverse. So you come to me and you say, I want a structure that has the following properties, but I don't know what it looks like. Find that structure for me. And this problem is ill posed, as we say, because there may be many structures that have exactly the same properties. So, how do I pick the one structure that has the right properties if there may be 25 that all have exactly the property you want? And this is why finding the right solution is mathematically speaking very complicated. We don't know what the solution is. And this is where, especially in recent years, artificial intelligence or machine learning has been a huge help. And this is what we've been using also quite a bit in recent years.
Just to get this right, you say that in the inverse process, there's many possibility for different structure that can give you the same exact behavior you're looking for. So what the differentiator in that case between all this similar structure?
Yeah, That's a good question. So, in print, I mean, let's take the example of a trust network like this one over here. And let's say that you come to me and you say, I want a very particular impact response. I want a very particular force displacement curve upon impact. Then, in principle, when we do the inverse design, I could come back with 27 or whatever different structures, and they would all match the curve that you want. But they may look very different. The structural connectivity may be different. The density may be different. The design may look different. And then, first of all, it's a challenge to find those 27 or more. This is what we handle with machine learning a lot. But then what you would typically do is you come up with secondary design criteria. For example, if you have those 27 structures, you could then go and say, well, okay, but I actually realized that I have some secondary objectives that I want to satisfy. For example, I want it to be lighter than something, or I want it to be printable, right? The printer may have constraints. You can actually not produce this funny structure. This is a problem. Or I don't know, this is great for loading it once, but if you load it cyclically over and over again, your structures may fail easily. So in this case, you have a range of structures that have the properties you want, but you may realize that other properties, of course, are different among these 27. And then you can start to either come up with secondary objectives or to pick and choose based on printability and these kind of things.
Interesting. So maybe quickly, in the range of the design, you have like minimum, maximum, like in the design for how many iteration, because you have to go for, and then you have to take each one and have to do empirical work to see the printability. I'm not sure what kind of printing technique you use, like SLS or SLA in that case, or something
Yeah,
else.
we play with all kinds. I mean, we try different ones. SLA, SLS, indeed, are the ones that we use more frequently. But in principle, I mean, for us, um, I mean, it sounds a bit boring, but our primary job is the modeling part. Of course, we often then also verification and validation by experiments to test it. But we often work with others who then, in the end, would try it out in applications and see where it goes. Our main task is to come up with a framework, computational framework that actually predicts what the structure looks like, and then to improve this step by step. And so, to get back to the question, how many iterations and how does it work? Um, it's a bit hard to say in general. One of the nice things about using generative modeling, this is what we do with AI, is that it's not like incremental topology optimization, but it actually spits out the structure at once. Once so the way it works is you first train a model based on many different architectures that can potentially be explored. So you first create a large data set where you have many different structures with different designs, different properties. And then you train a neural network or a autoencoder or some kind of machine learning model, and you train it to learn the inverse, how to go from property to structure. But once you have trained it, you've more or less done the bulk part of the work. And of course, you have to optimize the model and whatnot. But then it's super fast. Then you can go and say, I want these properties. And, within a fraction of a second, it can actually spit out the final structure. It's not that it has to incrementally somehow do optimization and then come up with a design that evolves over time. It actually spits out one or multiple designs instantaneously almost, which has another advantage we can chat about, but that's a different story. Um, and based on this, you get the prediction very fast. Of course, then if you want to test it, you want to try it, you may have to do this multiple times. You can improve it as you wish. But the nice thing about the generative AI is that it's really fast compared to classical incremental optimization schemes.
Hmm. And can you tell me about the limitation? You mentioned need the printability, but any other limitation comes to the metamaterial design?
I mean, of course, like any other technique, that there are many limitations. Printability or fabricability clearly is one. Often we have awesome designs and the thing predicts you should really print this one, and it just doesn't work because there's a severe of an overhang, there's some disconnected parts or whatnot. This just doesn't work. That's clear. Um, One also has to be careful that, especially if you use generative AI or use AI in general, it's a great tool to interpolate between designs, but one has to be careful when it comes to extrapolation. Which means if you create the training sets, you create a large data set of all kinds of structures that your model has ever seen, then the model can nicely create something that is somewhere contained in this parameterized design set, but it couldn't necessarily go beyond that. So if I train a model based on beam or trust based networks, it could never predict something that is made of shells, of plates, or something else. And so the one limitation to begin with is how do you parameterize your design? And we've done this for trusses or for beam-based structures, for example. And there you have to carefully think about how many beams can I take into account? How can I connect them? What do I assume about what happens at the junctions and so forth? We've also done it for shell-based designs, but then you have to carefully think about again how to parameterize the space so you don't get random nonsense, but you want to have a nice parameterization of your design. Um, that's a clear limitation that you begin with. You have a certain space, and then of course also there are a lot of physical constraints. I mean, I could not make a structure by saying I want something that is stiffer than the base material. Because if I fill this with 100% the base material, it is as stiff as the base material. I cannot put in more material than 100%. I mean, there are physical constraints that just tell me that the properties cannot just be about anything, but they have to satisfy certain physical laws, physical constraints that you have to satisfy. Um, and other than that, I mean, I guess if you yeah, it's maybe a bit more philosophical, but if if you use machine learning for this, you have a nice model by the end of the day that could predict structures, but it's still a model. It's not a human being that has intuition or experience or creativity or something like this. Um, I think it's nice because it can overcome the limitations that we as humans have. This is one of the nice things. One thing we learn, for example, is when you make these beam-based networks, very often, small changes in design can give rise to very large changes in properties. There's a very simple example. If you have a vertical beam, a vertical column, and you apply force to this, it's very stiff. If you take the midpoint and you move it just by a tiny bit to the left or to the right, and you now compress, it's going to collapse very easily. So a very tiny change in design can give rise to a very big change in property. And this we see very often. Sometimes when we do optimization, we start with a certain guess and we'll say optimize this for negative Poisson's ratio or high stiffness for some property we want. And very often the design changes are very small, but the change in the properties is huge. And this is something that goes against our common intuition. And if you as a designer, if someone as a designer wants to do this based on experience and intuition only, you very often miss some of these design opportunities simply because we think in our logical fashion. We don't think outside the box, and that small changes can give rise to big impact. And this is something where the models are actually quite nice because they somehow take this into account, and they do learn how to make small tweaks and perks to give you large changes. But again, they're not interpretable easily. You have a black box at the end of the day. We ship in properties that spits out a structure or design. But it's not that we learn design principles or everything like this. And this is a clear limitation of just the process as we use it.
I really like this point about how when you mentioned small tweaking in the structure or in the geometry could lead to significant change in the behavior, the structure of behavior. And maybe from your experience in work, did you had like situation that you already like was counterintuitive in the design, or you missed it sometimes in the initial basis, uh, working closely with the generative design? So do you think that's a trade-off sometimes is like for you when you try to make the initial guesses, or maybe the generative design sometimes it give you something counterintuitive? What I go with that? Yeah.
No, absolutely. I mean, in fact, I would say so. This is, I think, one of the strengths that these models also have, because if you use classical techniques like topology optimization or so, these are great methods, don't get me wrong, but they often depend on the initial guess. And the initial guess is very important because if you use topology optimization, you're basically exploring a little space, but you always try to find a minimum or a maximum or whatever optimum that's nearby. You never explore the full space that you can. And so, what we can do with these techniques is, in fact, we can spit out some design guesses, and those can then be used as initial guesses for further optimization. So, in fact, you could use this as a tool to give you, without the need for intuition or experience, whatever, 10 different initial guesses. And then you could use those to further do topology optimization or whatever to make them even more perfect. Because one of the things we also learned is these machine learning models are never perfect. There may be issues, there may be things one has to consider, one has to fix possibly, but they make for great initial guesses. And we had a number of cases where, as you were asking, the initial guess. One example we published last year, I think, is if you make these trust structures, one of the properties that sometimes is interesting is negative Poisson's ratio, or oxidicity, so called, which means if you take the structure and you compress it, normally it gets fatter in the other directions, but negative Poisson's ratio means you compress it and also gets thinner in the other directions. And this is something which sometimes for applications is interesting. If you want to make something that you have to prop into a small hole or something, right? You push and you want it to shrink and not to expand. Or the same is used also in stents for surgery on humans. You want to put it in, when you pull, it expands laterally and not vice versa. And so this negative Poisson's ratio has been known for many years, but the question is how to get large negative Poisson's ratios. And we did one study. We worked on these trust networks, and we took the full data set that we used for training, and these were on the order of hundreds of thousands of different structures. We simply picked the one that had the most negative Poisson's ratio. And we said, okay, this looks like an optimal guess. Let's go with this one. Then we did the optimization using our machine learning models, and it turned out we could make it by a factor of 2 or so more negative, go far beyond what we had initially, thought would be within the realm of what we're exploring. And so there we are at times quite surprised that these machine learning models, they interpolate in the design space, but it does not mean that they have to interpolate in property space. They can sometimes extrapolate a lot because exactly these small changes give rise to big changes in properties. And so there we've been surprised a number of times how we thought, you take the most negative or the most stiff or the optimal or whatever design, and then you run the models and do optimization on this, and they spit out structures that are much, much better than what you started.
Interesting. And for the negative pursuit ratio, can you tell me other use cases beside the shoe could be useful?
Yeah, so I mean, this is like I said. So one of the things is if you have something that there's one case that everyone knows from cooking. This is actually what this arises. If you think about a wine bottle, for example, and you want to close the bottle, it's typically closed with a piece of cork. This the thing in there. And cork is a very particular material because it has a Poisson's ratio of 0. Now, this even the old Romans and others have known, because what it means is if you poke on it, if you try to compress it, it does not expand laterally. This is what a Poisson's ratio of 0 means. And that's exactly why it's used for wine bottles, among others, because when you press it in, it does not get fatter. Because otherwise you would never get it in. You press, it gets fatter, it gets even worse. You press more, it gets fatter. It would be, a vicious circle. You cannot get into the bottle. A positive Poisson's ratio would be bad. That means you compress, it would get fatter, it doesn't work. For cork, it's 0, that's okay. But if you now have something where you want to press and it actually goes through smoothly, so you have an application where you need to press something in, but it shrinks. This is exactly where negative Poisson's ratio is the method of choice. Another one, like I said, is biomedical applications for stents or things like this. In those cases, a stent is nothing else but a mesh made out of a piece of metal or so that you want to insert into an artery. And typically you insert it, but then what you want to do is you want to inflate it so that the arteries open up. If there's plug, the artery is clogged, you want to open it up again. If you insert something with a negative Poisson's ratio, then you pull. What happens is you pull and it gets fatter in the cross section. And then all you need is a very little force, and the thing pops up and opens the clogged artery. There's another application. There are many other ones. Um, Filtering devices, for example. If you have something where if you pull one way, it doesn't shrink, it actually opens up the other direction. In this case, you could make a sheet with holes, and when you pull on it, these holes open up in all directions. So you have a device where all you need to do is control it in one direction, and you have holes that open up or close. This could be used for, or is being used for filtering devices, among others.
Interesting. Maybe
There's a
in
lot.
yeah, a lot list. But since you have been working in different use cases, if there's any problem was really hard to solve. And I think one of the things I would like maybe to share with you, like for example, designing multi-material with higher toughness and delaying damage propagation. So if you have two different material and you want to make certain geometry, and I'll give example in nature like the seashell, for example. I think there's many people done research in that area. Another creature in nature, they have this kind of arrangement for different material. that do this trick to light damage propagation. And I'd like this design. And actually, it was part of my PhD thesis. But I want to ask you: do you think it's a challenging problem for mechanics if we have to like do different material or many materials to do different behavior, like higher toughness or delaying damage? Yeah.
No, sure. I fully agree. I mean, fracture toughness, in fact, is something we have worked on also more recently. Not in the context of multi-materials, but also in the context of structures. But it's a very similar thing because this is a multi-material. It's basically polymer and air, right? It's two materials, if you want, put together. You could also, with 3D printing, you can very easily do multi-material printing as well. And then you have different types of materials in the struts or on the plates or whatever. So no, I think definitely this is quite interesting. One of the things that we learn a lot is that when we classically think about fracture, we typically in mechanics we think about homogeneous materials. You have a piece of whatever metal, a piece of polymer, you pull on it, and then a crack propagates, and this is how we think about fracture. And in classical mechanics, there are theories for this. I mean, people studied this 100 years ago. We know fracture mechanics very, very well. But typically, what happens is if you apply your fields to the thing and you have a crack in there, then at the crack tip, usually you have very, very high stresses and strains. We call this a singularity. The stresses grow almost infinitely because of the sharp crack tip. And this gives rise to exactly the crack behavior that we typically see in a solid. Now, if you have a discrete structure, be it a truss or be it a multi-material a network where you have different types of constituents put together, the picture changes a little bit because let's take the truss as an example. If I introduce a crack here, you can easily do this. We can pull on the thing and see what happens. But out of a sudden, at the crack tip, I don't really have a sharp tip and a material anymore. I just have a number of beams. And so what happens now, I don't have this infinite stress concentration anymore, but I just have one beam, and I need to look at when does this beam fail. And in this case, the behavior can actually be quite different. There are certain materials which, in principle, are isotropic, meaning that you can load them in different directions. They always behave the same. If you do this with these types of materials, they may be isotropic, but once you start rotating and putting a crack in, they behave completely differently. Somehow, this discreteness at the crack tip matters. How do you arrange the material at the crack tip relative to the crack? Do you have a beam that's straight? Do you have beams under angles? This makes a huge impact on the fracture toughness. And it's quite similar if you go to multi-material structures. You again have a crack tip and the crack wants to propagate. But now, if it starts propagating, the question is what happens? Is it just going to see the same material and go through? Or is it going to encounter, let's say, a stiff inclusion and it has to go around it? Or is it encountering a gradient in stiffness, a gradient in plastic behavior, or whatnot? I mean, this people have looked into this. In fact, we did a study on non-periodic trusses, but there's been quite a bit of work on trying to optimize architecture for improved toughness. Exactly taking inspiration from nature, as you said. And in many cases, I would say nature is smarter than we are a lot, and it has built very very interesting structures across scales. And if one can leverage this to get optimal behavior, of course, I mean, I think there are
Mhm.
huge opportunities.
Awesome. Since it goes and answer your question, coming to the back, the bike, the helmet, it's resolved with injuries. What still you think could be done? So, like, I assume the pressure distribution, redistribution inside the helmet, or what exactly that you've done in this example?
Just to be straight, I never designed a bike helmet. Right, we work on structures for impact absorption and so forth, but the bike helmet itself, I've never worked on. But especially when it comes to impact absorption and these applications, there are a number of things one can work on. One, of course, is you want to optimally protect what's inside. So you want to absorb. This actually is a good example for a material where if you have an impact, it absorbs a lot of energy. Then, of course, you want to make sure it does so at relatively low weight because you don't want to wear a helmet that weighs 10 pounds or so. This is another consideration that always is on the table. You want to be you want it to be ideally reversible so that you don't throw your helmet away every single time it falls on the ground or so. So it must be something that you can periodically load, and ideally it should resist without major damage. Um, and then, especially for the bike helmet, there are interesting studies out there that look at how the head and also the brain responds to different types of impact. And it's not just the force that matters. It's not just the impact. It matters how it's being, rotated, how it's being translated. It depends on the rates that act. It depends on what hits your head. There are whole studies on the skull of, how ideally to not impact the skull and so forth. And again, I only work on making structures that have certain properties, but if you take into account what is needed, and this needs to be addressed by physicians, by therapists, by surgeons and whatnot, then the goal is to make structures that are as lightweight, as energy absorbent as possible, while taking into account all kinds of other constraints.
Interesting. So I think maybe I want to ask you, anything is a challenge so far regarding what you're doing? You mentioned already maybe the printing techniques, maybe is still maybe something, and still SLA. There's companies, maybe they had the proprietary machines and their materials. So I think I'm not sure what your take about that. Um, and maybe other
Yeah,
things. Yeah.
no, that's true. So I agree. It's of course, I think fabrication manufacturing still is one of the bottlenecks nowadays. One thing that's interesting, and I guess this is progressing more and more, but it's very easy to make these structures at the scale that I'm showing you here. Right? These are relatively large. We can try to miniaturize them and make them smaller and smaller. There have been really nice studies from a bunch of people in Europe, in the US, and China, all around the world, um, that use small scale fabrication. If you use, for example, nowadays two photon lithography, it's a nice process where you can print things at teeny tiny scales. And it's not nozzle based or powder based as we typically do at large scales, but for two photon lithography, the idea is that you have a liquid resin, so you have a liquid polymer essentially, and then you have two laser rays that shine into this basin. And at the point where the two laser rays meet, you have the highest laser intensity. And if you control this very carefully, you can have significant intensity there, sufficient intensity to solidify the polymer. And if you do this very carefully, you can basically let the laser rays move around, and wherever the laser ray walks by, it solidifies a structure. And everyone does this carefully, and there are nanoscribe and competitors nowadays that you can get, you can just purchase a printer if you have a lot of money off the shelf. And these can print the structures down to nanometer scale. So one can make the same kind of thing where each unit cell is on the order of 100 nanometers or 500 nanometers or something like this. And then it becomes really interesting because then it doesn't look like a structure anymore. Then to the naked eye, it will look like an actual material because we don't see the small scale features anymore. And with this one can do tremendous things. For many years, I worked with a good friend and colleague at Caltech, Julia Greer, and she makes these teeny tiny structures at the nanoscale. And they've made structures that are even light enough. You can put it on a what do we call it, a daffodil, on top of flowers and whatnot, and it would just float. If you leave it in air, it will float because it's so extremely light. It has 99.9% air or so, and it's made at such small scales that with the naked eye, you don't even see it's a structure anymore. It really looks like material. That's where the metamaterial again, is a good name. Um, and those are fantastic for many applications, but there the problem is the scalable manufacturing. Because if you try to make all of this at small scales, you can, but to make a cube that has whatever 50 by 50 by 50 unit cells, it takes a few hours. And if every unit cell is 200 nanometers and you can at most do 50 by 50 by 50, right? That means you're far away from just a millimeter. So we can make large structures, but they have very, discrete behavior, very discrete features. One can make very small structures, and they are fantastic because they look like a material, but you can only make micrometers out of this. There's no way we can use this to design a large plate or a helmet or something else. And this, I think, is still one of the bottlenecks trying to come up with scalable manufacturing techniques where you can really make large structures that have small features that you design a priori. Um, there's a lot going on, to be honest, in this field. From self-assembling structures to spontaneously decomposing structures and whatnot. So I think there's still a lot to expect for the next years to come on. But these fabrication constraints clearly are limiting. Also, the number of materials we can use. With polymers, it's relatively easy. If you want to do the same with metals, of course, it gets a lot harder. Ceramics is also quite hard. But even this is developing. I have a good a colleague here at ETH, he's now printing or 3D printing hydrogels and even living cells. So you can print the same thing, but inserting human stem cells, which will be fantastic for bone implants, for example. Um, there are techniques now where you can pyrolyze those, which means you make a polymer first, then you put it in a vacuum and you burn it. And then what happens is this polymer is turned into carbon. Then you have something that's made out of pure carbon, which one couldn't do easily 10 years ago. It's a number of materials is increasingly growing. Also, active materials. There are colleagues in the Netherlands, for example, who use piezoelectric materials to print structures. And then you have structures that can respond to electrical stimuli, which is super interesting as well, especially for robotics. Then you can make structures where you apply an electric field, and all of a sudden, they change features based on applied electric fields. Oh, by the way, that's another
Yes.
thing I could talk. Uh,
Oh, no, straight out here. What is this?
sorry,
What is
just
no, what,
yeah, I hadn't. So this is a project we've started more recently in recent years, and these are nothing else but straws. If like the drinking straw that as a kid or like to drink a cocktail you put in, and but they're super interesting from a mechanical or also soft robotic perspective, because these structures have a huge number of stable equilibrium configurations. So this is nothing else but a straw, and I can transform it. But the nice thing is I can turn this into all kinds of shapes, and it stays those shapes. And especially, I'm sorry, this is loud. If you fully expand, these things can assume almost anything you want. And if you design this very carefully, you can make anything from grippers to tactile haptic devices, all the way to snakes that go into certain corners. And a number of people who've looked into this, there are colleagues here, also at the Technion elsewhere, um, and many people use them for soft robotics. What we do here in particular is we look at the mechanics behind this, meaning how can you make interesting straws that give you properties you couldn't find elsewhere. For example, this one is circular. We can make them with all kinds of shapes. If you change the shape, you can make that one end goes only left, one end goes only up, one end does something else. Or also, can you design the deploy sequence? Can you make that it's not random, but can you make that it starts from here and then goes through there? And with this, you really have a tremendous opportunity to design things that reconfigure upon stimulus, things that you can store, but if you want to, deploy them and you have a huge structure. This can be used for anything, from space structures to things on Earth where you want to deploy something, restore it small, and then you deploy it. Or you want to have an arm that goes somewhere, or you want to have something that grabs. And what's nice about the structures and these soft structures we've been working on for a number of years is that, in principle, this gets by without any electronics. If you design it carefully, you can use air pressure, you can use fluid pressure, you can use other things, but you don't need electronic devices, which means you don't need metallic wires that could debond and fail. It means you don't have necessarily a complicated access control circuit, but you can do it like in soft robotics, where you try to design soft devices, all soft devices without metals, without actuators behind them that perform a certain function, but without you controlling it actively, with some kind of electronic control circuit. And there, I think there's still a lot to come. I'm not a roboticist, which is why I'm invited here because I'm really not a soft roboticist. I'm a mechanician. But I think even in our area, we can contribute a lot so that others can explore it, explore and exploit these features.
awesome. So maybe the question, maybe the first one in your career, there's moment like was very challenging in your career. I know you had a stellar career that, uh, like moments was like doubting yourself, like doubting yourself. It was very
Very
hard.
often. I mean, that's a good question. I think one of the things that, especially in academia, I don't know how it's elsewhere, but there's the so-called imposter syndrome that affects I don't know how many of people, and you feel like, oh, you don't know anything. And especially in science, I mean, this happens to be a lot because there are so many things we just don't understand. I can give you one very simple example with this thing over here. We still don't understand it to this day. We're looking into it. We think we understand, but you never know. If you do just this, you bend it to one side. If I now move it around, I notice that I need a significant force to move it. Otherwise, it would stand still. But each of these configurations is equivalent. There shouldn't be any force. Theoretically speaking, there should be no force because it's all equivalent equilibria, but we feel the force. And for weeks, we've been discussing, we've been looking into things. We just have no clue why and how. Eventually, of course, we come up with a theory. And this happens so many times that you think you're dumb and you have no clue of how it works. Or we do experiments and simulations, and you won't believe how many times they don't agree. And then you have to figure out what is wrong. Is it the experiment? Is it the simulation? I mean, these things we have all the time. And another thing that's very annoying about science is that, of course, many people around the world work on similar things. And especially have hot topics like AI in design and mechanics and so forth. Many groups around the world work on similar issues. And you can work your butt off for a year on something, and before you can submit the paper, someone else publishes something very similar. And then you get gray hair. This happens a lot. I don't have the perfect answer to this. We just try to do good science. I think one of the things I try to do is to I personally try to recruit the best people for this. I mean, I've been blessed in my career, both at Caltech and now here at ETH. I've had a very long list of really outstanding PhD students and postdocs. And I think a lot of what we do, of course, I owe and the team owes to them because they come with creative ideas and they come with motivation, stamina. Very often, I'm sure it's much more frustrating for them than for me. And I think this is really what makes a huge difference. If you have a fantastic team you can rely upon and who's excellently qualified and motivated to do it and to never give up, even though it keeps failing for 3 months in a row, and then finally it works. This I think is the key factor number one to me. And then of course I think you just have to be open to new things all the time and just try things out. If it sounds interesting, try it out. I think this honestly is one of the advantages I have here in Switzerland, if I can say this on live whatever podcast, but um, that we do have funding to try things out, which is not always the case. And if I compare the American system to the European system, there are some significant differences. Of course, we're not rich compared to others, but just to have the possibility to every now and then have a student try something out of the blue because you want to, because you have the idea, because they have an idea, because you jointly came up with something new, and you try it out without the need to please a funding agency immediately. This is an absolutely luxury benefit that I see that we have here, and this helps a lot. Uh, yeah. And otherwise, I mean, I guess one just has to stay on top of publications and conferences and see what's out there. I would say if you're maybe two things, right? The one is I want to take you up on what you just said, because I think we all know that we have these is we're going to run into trouble all the time. But I think the important thing is to never give up and just never think that you're little and you don't know something and everyone around you is so smart. I mean, this happens to all of us all the time. Some people don't talk about it, but I think it happens to so many of us. Just never give up and keep going because it's going to work in the end. But the second thing is that more on the topic. I think this the concept of making of using architected materials or structures is has been around for a while, but it's still growing. So if anyone is interested in this, it's very easy to get into, because for this you don't need quantum mechanics. You need some very basic mechanics that we learn in undergraduate mechanics and most engineering programs. You need good manufacturing techniques, but nowadays 3D printers are cheap, and so there are many opportunities. And of course, here I talked about a lot of high-end techniques using ML with computation modeling and whatnot. But sometimes there are low-hanging fruits of doing this too. For example, I now have a fantastic PhD student who is looking into optimizing the feet of a legged robot, because we have colleagues that work on legged robots that walk around, and the feet of those, typically you just use whatever piece of metal, piece of polymer, piece of something, but that piece of something can cause, for example, significant vibrations. It doesn't absorb energy appropriately and so forth. So now she's looking into how to make structures of this type that give you the optimal impact rebound and the optimal vibration suppression for a legged robot. It's a relatively simple thing to try, but with these structures, you can do almost anything from soft to stiff to strong and tough to whatnot to reprogrammable and whatnot. So I think there's really huge opportunities for these kind of structures. If anyone wants to get into this, it's relatively easy. So